The ear is divided into three areas: external, middle, and internal. The external ear is comprised of the auricle, helix, lobule, and external auditory meatus, which are made to capture sound and funnel it into the middle ear. The middle ear is comprised of the tympanic membrane, malleus, incus, and stapes. The tympanic membrane vibrates when sound hits it, causing the malleus to impact the incus, which moves the stapes, conducting the sound into the oval window of the cochlea. The internal ear is comprised of the cochlea, vestibule, and semicircular canals. Sound is transmitted into the cochlea's endolymph via the oval window. Sound passes through it and causes certain regions of the tectorial membrane to be activated depending on the pitch. The sound exits via the round window below the oval window and stapes contact point. The semicircular canals, while not involved in hearing, do sense movement and balance. The saccule detects gravity and linear acceleration. In order for sound to be registered by the brain, the auricle, helix, and lobule capture the sound and conduct it into the ear. The sound travels into and down the external auditory meatus until it impacts the tympanic membrane, which begins conduction into the middle ear.
The middle ear's function is to conduct and amplify sound into the cochlea. Sound waves pass through the external acoustic meatus, and the vibration moves the tympanic membrane. The tympanic membrane pushes on the malleus bone, also called the hammer, which causes it to impact with the second ossicle bone, the incus or anvil. The incus then impacts into the third ossicle, the stapes, which is also called the stirrup. The stapes pushes onto the oval window of the cochlea. Pressure waves are created in the perilymph of the scala vestibuli, which are transferred to the endolymph of the scala media. The tympanic membrane is thin and very fragile. In order to keep it from bursting due to pressure changes, a small tube connects the middle ear to the pharynx. This is called the Eustachian tube, and the pop you hear when you go up or down in altitude are pressure being relieved and localized in the middle ear.
Sound is transmitted into the cochlea, an organ in the shape of a snail shell or spiral, through the oval window. The vibrations then cause hairs on hair cells to vibrate and move depending on the pitch of the noise. These hair cells are located on the organ of Corti, which rests on the basilar membrane and below the tectorial membrane. These hairs, when made to vibrate, contact the tectorial membrane, which triggers the sending of action potentials to the brain via the vestibulocochlear nerve. The brain then interprets the messages into sounds and interprets them to either a car horn, or your mother scolding you, or even your favorite song. Since the endolymph of the cochlea is not easily compressed, the round window below the oval window provides an exit for the vibrations that enter the cochlea. High-frequency waves displace the basilar membrane near the base, where the fibers are short and stiff. Low-frequency waves displace the membrane at the apex, where the fibers are long and flexible. The short, thin nature of the high-frequency hairs is what makes them so brittle and easily breakable. This is why the higher range of hearing is usually the first to go when the hairs are damaged, or from old age, as the hairs don't ever grow back.
The semicircular canals are important to equilibrium and rotational acceleration of the head. There are three semicircular ducts, which are the anterior, posterior, and lateral. The vestibule is made up of the utricle and saccule. These are important to static equilibrium and linear acceleration of the head. The lateral canal senses transverse rotation of the head by sensing signals to the brain when the endolymph inside the ampulla moves the capilla by passing over it. The superior and posterior semicircular canals also function in the same way, but detect for sagittal motion and coronal motion respectively. Otoliths in the saccule of the ear also aid in hearing, but are detectors for gravity and linear acceleration based on slight changes of position.